Welcome back, everybody. I wanted to get started with new material today, so we're going to start looking at section 9.7. Ultimately, this deals with the law of sines and the law of cosines and solving for triangles that aren't right triangles, but I think there are a couple of steps that we should get to before we start talking about those. The first has to do with finding the trigonometric ratios of obtuse angles. Up to this point, we've only looked at right triangles and looked at their acute angles, but it turns out that we can find the trigonometric ratios for any angle whatsoever. I'm going to see if I can show how this works by looking at a specific example, namely the one in this first diagram right here. Instead of having right triangles just floating around in space, let's imagine them in the coordinate plane. Specifically, let's imagine this blue right triangle with one 45-degree angle at the origin. Since it's an isosceles right triangle, we know that its side ratios are going to be a, and a times the square root of 2, whatever a happens to be. Now let's think about reflecting that triangle to become the orange triangle in the second quadrant. An important thing to note here is that this side that was a units long is now, interestingly, negative a units long. And this all comes from the fact that all x-coordinates in quadrant 2 have negative values. But we should also remember that the y values are all still above the x-axis. And we see this playing out in the orange triangle. So where we had negative a units for this horizontal side, we still have positive a units for the vertical side. This is a completely new idea for us. We've only ever dealt with lengths having positive value, but once we start to put things into the coordinate plane, we have negative x values, we have positive x values, and negative and positive y values. So we can start to talk about what it means to have negative distance. The most important thing of all in this figure, however, is the fact that the hypotenuse of the orange triangle is still positive a times the square root 2 units long. And that comes right out of the Pythagorean theorem. Negative a squared is the same as positive a squared. Okay, I want to add to this idea the idea that we can actually measure angles that are obtuse angles within this diagram itself. So I've redrawn the diagram somewhat transparently down below. And let's think about that 45-degree angle that was formed at the origin in the blue triangle as really being measured from the x-axis up to that ray that forms the other side of the triangle. That would be 45 degrees. In fact, we can think of all angles as being measured this way. The 45-degree angle in the orange triangle we can actually think of in another way, because it's supplementary to an angle that begins along the x-axis here. So if we start at the x-axis, we can actually rotate around in this direction and create the same angle. Of course, this angle is going to be supplementary to that 45-degree angle. So we can think of that same angle as being 45 degrees with relation to the negative x-axis, but we can also think about it as being 135 degrees with respect to the positive x-axis. So in the coordinate plane, there's really nothing different between these two angles. That 45-degree angle that's made from the negative x-axis and the 135-degree angle that's made from the positive x-axis. But here's where things get particularly interesting, because we can talk about the trigonometry of these two angles, the small 45-degree angle and the large 135-degree angle, by referencing the side lengths of the blue and orange triangles. We know that the tangent of the small 45-degree angle is a over a, or 1. But if we look at the tangent of the 135-degree angle, we're now looking inside the orange triangle. In fact, we call the orange triangle a reference triangle, because it's the triangle that would be created if we took our 135-degree angle and created an altitude in the second quadrant for that. So we discover then that the tangent of 135 degrees is related to that orange triangle. But that tangent has a positive a for the opposite side and negative a for the adjacent side. So we end up with a over negative a. That's equal to negative 1. Now take another look at that orange triangle and look at the cosine. So the cosine is now going to be this negative a, the adjacent side, over positive a root 2. Well, those a's cancel, and we get negative 1 over the square root of 2. Now we can rationalize the denominator, and that becomes negative square root of 2 over 2. So the cosine of 135 degrees actually turns out to be the opposite of the cosine of 45 degrees. And all because we can measure these angles starting at the positive x-axis and going counterclockwise. And because within the coordinate plane we can have negative x values and negative y values, we can end up changing the sign, S-I-G-N, not S-I-N-E, from positive to negative or negative to positive, depending on the angle and where the terminal side of the angle goes. We call this the terminal side, if we're considering all angles starting out along the positive x-axis. Let's take a look at a couple of quick examples here to see how this actually works. Maybe we'll draw out a couple of sketches. So the key point is that we start drawing angles at the positive x-axis, and then wherever that angle ends, we create a new right triangle. Sometimes that right triangle has negative side lengths. Let's see how that'll work out. So let's consider this first problem, where we have an angle measuring 92 degrees and an angle measuring 88 degrees. Let's draw out this scenario. Now both of these angles are incredibly close to being right angles. So if we take the 88 degree angle, we can start at the x-axis and create an angle that's 88 degrees. Let's say it looks something like that. It's a little bit exaggerated, but this is 88 degrees. Now if we want to create a reference triangle or a right triangle that'll tell us the trigonometry we need here, we can just create that right triangle in this way. Now we know that in the x direction, this is going to be a positive number of units, and this is also going to be a positive number of units. So it should be the case that our sine, our cosine, and our tangent are all positive in this particular case. And if we check them out on the calculator, we'll see that that's probably the case. So let's find the sine of 88 degrees. 0.9994. We'll round that off at 4 decimal places. Definitely a positive number. And in fact, we can do exactly the same thing with cosine and tangent, and we'll fill those in here as well. Alright, so much for 88 degrees. But let's try 92 degrees. Let's draw that angle in. We can start, again, right along the x-axis. Let's say it goes in this direction. Again, a little bit exaggerated. But this angle is now our 92 degree angle. We can create a reference triangle here pretty easily. And in this case, we're going to have a negative motion in the x direction and positive in the y. So it should be the case that the tangent's going to be negative, since it's going to be a positive number divided by a negative number. The cosine's going to be negative, since it's going to be a negative divided by a positive number. But the sine should stay positive. So let's take a quick look at how these look for 92 degree angles. And we see that just as we expected, the cosine and the tangent are both negative while the sine remains positive. But even more significantly, the cosine of these two supplementary angles, the tangents of these two supplementary angles, and the sine of these two supplementary angles all have the same magnitude. It's just that they become negative for angles in the second quadrant and remain positive for angles in the first quadrant. And let me be very clear, when we're talking about angles in the second quadrant, we mean obtuse angles, because those angles will measure between 90 and 180 degrees. I'll leave numbers 2 and 3 to you, but just remember the rules that we found here about supplementary angles and how their cosine, tangent, and sine ratios align with each other. In the next video, we'll figure out how to find the area of triangles using trigonometry. Thanks, everybody.